Today we're going to take a look at section 1.6, which is called Formal Definition of a Limit. And I want us to start, and depending on when you printed this out, there's probably a typo on your paper. I found it yesterday. This should say the limit, consider the function f of x equals 5x plus 2. So if yours says 3x, just change that 3 to a 5. I fixed it last night. So 5x plus 2. We're going to consider finding the limit as x approaches 3 of 5x plus 2. Now, when we did this in section 1.3, we actually found that the limit equaled 17. How did we do that? Do you remember?
Plugged in the value.
Yeah, we plugged in the value. And we said we'd actually be able to do that because this is a polynomial. Polynomials are continuous, which we did that in section 1.4. And so we were able to evaluate this into the function simply because it didn't cause any sort of problems, basically, right? The function value and the limit were the same thing. Intuitively, this makes sense to us. Right? We talked about this from a very intuitive point of view. But this description is very imprecise mathematically. In fact, when we first defined limit, do you remember how I described what a limit was? I gave this sort of an intuitive description where I said, a limit is a y value you get really close to and you may or may not touch. Do you remember that? I think that I have colleagues that would just be appalled that I told you that actually out loud in words because it's so not mathematical. It's very imprecise. It's very intuitive. It gives you a good visual image, at least I hope it does. That's my hope in doing that. But it's not very rigorous. It's not very mathematical. That's what this section is going to do. It's going to firm up our definition of what it really means to talk about a limit. So we're going to start by considering this particular graph, okay? So as I graph this and you graph this, what will this graph look like, generally speaking? A straight line. And I'm not going to worry too much about my units on this, simply because it's not all that important. But at some point along the x-axis, I have the x value of 3 that I'm talking about approaching. And if I trace this up, I actually have a point on that y, or on that curve. And supposedly, according to the limit that we've decided, this value is actually at 17. Everybody good with that so far? Okay, so the idea behind what we're doing today is that we're wanting to make sure that as we get close to the x value of 3, we're also getting close to the y value of 17, that happens sort of simultaneously. And what we're saying is, let's say that we only want them, this is not so good, that is the y value, or the y value that we're approaching. Say that we only want our y value to be 1 unit away from the 17. Okay, so we want our y value to be between 16 and 18. Okay, so over here my picture, and I'm going to exaggerate what I'm doing just because it'll make it easier to draw the picture. Here's 18, pretend, and here's 16. So we want my y value to occur somewhere between 16 and 18. So the question is, if I were to trace over on my graph and down here to my x values, again, there's nothing about this that is drawn to scale. I did not do any kind of scaling. Okay? The question is, what x values, or how far away from 3 could I actually be on the x-axis to make sure that I'm only 1 unit away on the y-axis? Are you with me? So that's the idea of what a limit is. The idea of the limit is that if I get really, really close to the value of 17 on the y-axis, I should be really, really close to the x value of 3 on the x-axis. I'm not using the right letters today. Let me say that one more time. If I get really, really close to the y value of 17 on the y-axis, I should be really, really close to the x value of 3 on the x-axis. Okay? But the question is exactly how close do I need to be? In other words, how close does putting my x or my y value close to the 17 force me to have to be close to the value of 3? And that's what this is actually doing for us, or describing. So let's take a look, and we're going to consider that y value of 1. So if I want my graph, which is 5x plus 2, to be really close to a y value of 17, that is, I want the graph and the y value of 17 to be only 1 unit apart. That's what this 1 over here is saying. Then a question is, what number needs to go in here? That is, how close do x and any x value and the x value of 3 have to be to make that happen? Okay? Well, that answer is actually a little bit of an algebra situation. So take a look right here at this inequality, and somebody tell me what's the first thing I do to solve that inequality? Combine like terms. What can I combine, Blaine?
2 and negative 17.
And what will that give me?
Negative 15.
Perfect. Okay, so right now that absolute value, the value inside becomes 5x minus 15. Everybody good so far? Okay. And then what? Yes and no. We're actually not going to find the exact answer, but we would if we were actually finishing solving this for x. But what we are going to do is we're going to notice that the 5 and the 15 have something in common, a 5. So what I am going to do is I'm going to factor out a 5, and I'm going to draw this a little bit differently simply because your homework will make it helpful for me to do this. So I'm pulling a 5 out, and I've written it in a funny way. This is actually the absolute value of 5, but what's the absolute value of 5? It's 5. Now, what if this had said negative 5? What would be the absolute value? 5. Okay, so keep that in mind. You've got a homework problem that will employ that issue. And then what would I do? Any guesses? Divide by 5. Now, this is actually what I wanted to have happen. I wanted to solve this actually for the absolute value of x minus 3. I didn't actually want to solve for x. Do you guys see that?
Okay.
So that's why I headed this route. I wanted to simplify this into such a way that I end up with the absolute value of x minus 3 instead of ending up with x equals. That means that the 1/5 is what goes in the blank over here, right? Everybody good with that? So 1/5 is what goes over here in this blank. So in other words, back over here on this picture, if I want to be within 1 unit above or 1 unit below on the y-axis, I can only be within 1/5 unit to the right or 1/5 unit to the left on the x-axis. That's what that told me. That actually tells me that these two question marks, these look like 7s, they're supposed to be question marks, down here actually occur at 3 and 1/5, and technically then 2 and 4/5. That's what that tells me. Okay? It tells me that this distance in either direction is actually 1/5, whereas these distances up and down were at 1. Everybody good with the visual imagery so far? Because we're about to make it a little bit more abstract. Okay? There was nothing special about choosing a y value that was 1 unit away. Nothing at all. I chose it simply because I had to choose something to show you a picture that you could relate to in terms of numbers. So instead now of doing this with 1 unit above and 1 unit below, we're going to say that we're going to do it a variable amount, epsilon above and epsilon below. Okay? Epsilon is simply a Greek letter. Kind of like you're used to using x in algebra. You guys use x in algebra, don't even think about it. When those kids start x in algebra in, like 6th, 7th, 8th grade, they freak out. Maybe you were one of those freakouts too. You're like, what? Variables in math? What is this letter going on here? Epsilon is just a Greek letter, okay? It's just a variable. It has some features to it. When we use epsilon, we mean epsilon small. That's something inherent in what we're using. So epsilon's a very small number. It's also got to be positive. And if you look at this, it sort of makes sense that we need it to be positive because I'm talking about an absolute value here. So it's got to be smaller than a positive number. Is everybody good so far? We can solve this just like we solved it when the number was 1. It's not any different, right? I can actually change this just as I did before to 5x minus 15. I can still pull that 5 out. Again, it's an absolute value issue, but we discussed that the absolute value of 5 is 5. And I can still take this and I can divide it by 5. The only difference is that instead of in the blank having the number 1/5, what's the value I have in my blank? Epsilon over 5. And this name for this value, no matter whether it's epsilon over 5 or 6 epsilon or epsilon times 2.7 or whatever, the name for this location is actually the name delta, another Greek letter. And again, that other Greek letter is, again, the same thing. It's a small number, it's positive, all those same things, but it's just another small number. So sometimes what we're about to do, you'll hear called epsilon delta proofs, or the epsilon delta definition of limit, because we're using those Greek letters epsilon and delta. Okay, so I'm going to pause for a second. Have I freaked you out yet? Is everybody okay? This is the most theoretical section that we're going to do in this chapter, for sure, and by far. So let me show you the next thing. Next thing on the next sheet of paper, the back of your sheet of paper, is the precise definition of limit. Now, I want you to fill in the blanks, and then I'm going to talk through it. So first of all, just fill in your blanks, and then let's talk. All right, most of you are finishing up. So first of all, this is talking about a function being defined at the point A, or at least nearby to A. We have a limit value, it is L, and we have that epsilon, that small number greater than 0. So if we are able to say that the absolute value of x minus A is less than a delta, a positive number, but delta, and it guarantees that that f of x minus L is less than epsilon, then that confirms that our limit is in fact L. Now, once we use some functions in here, and I can put some numbers to what this is doing, it'll make it a little bit more clear. But here's what you need to know right now, and you need to write it down. I'm going to ask you to put this down verbatim on your test. You need to memorize this. It's not something that I do like ever in math. It's first of all to tell you to memorize the definition, and second of all to tell you it's going to be on the exam. I will ask you for this verbatim. There's good and there's bad with that. So the bad may be that you don't want to memorize this, and I get that. The good is that means that if you've memorized it and you come in and you've got it memorized, you know, get those points on the test, right? So that's actually sort of a nice feature. Now, as you work with the next problems that we're going to do, you're going to find that you're going to start to sort of memorize it by default already. All right, the more you work with certain things, the more you just sort of naturally memorize them. That will happen to some extent as you work with these next two problems and then your homework problems on this. But you've been forewarned. Make sure that you have memorized this. I will ask you to recite it, so to speak, or write it down verbatim on your test. Okay? All right. So let's actually talk about how these problems look, because what I actually did in the last problem is that I didn't sort of work through it in a very straightforward way. We bounced around a little bit. I used the number 1, and then I changed it to epsilon, and I never actually finished how the problem would really look if you were working the actual problem. But we are going to on the next example. So let's take a look at this one. Your directions say symbolically find delta in terms of epsilon. I put those directions in there because that's what your book actually says right here, exactly. Now, if you only do that specific part of the directions, you're not going to complete the actual point of the problem. So as you're doing your homework, please look back at these notes. What we're doing on these notes is what I expect to see when you do it on your homework, or if I ask a question like this on the test, what I expect to see on the test. All right, so here's where we start. First of all, it's probably a good idea to make sure that the limit value is right. Is it?
Yes.
Yes, it is right. So if we put the number -2 in, we do get -4. Everybody good so far? All right, great. So what we're going to do as we set up the problem is we need to set up the problem so that this value minus the limit value is less than epsilon. That's where we're working from. We're trying to find the difference in the y values, the function value and the limit value, to be less than epsilon. Now our goal, using the red here, is to change this so that the x value minus the x value we're approaching, that is, write the value underneath there, is less than some delta. So my goal is actually for this to say x plus 2. is less than some number delta. So as I'm doing this, it's sort of important to keep where you're starting and where you want it to end up in mind. I'm starting right here where this is written in black, and I want to change this in some way, shape, or form so that it becomes the piece that's in red. So far, so good? So let's do the algebra. How will that inside of that absolute value simplify? Combine like terms, so this will be 3x, and then what? Plus 6. Then what? We can factor out of 3, and it factors out positive, right? Oh, I have a typo there, sorry about that. There we go. And then what? Divide by 3. So we've actually found the x plus 2 absolute value is less than epsilon over 3. What that actually tells us is that our delta value is the same as epsilon over 3. So this is delta equals epsilon over 3. Now, the directions sort of make you feel like you've finished the problem. Agreed? Here's what I expect to see after you have found that delta, because this is what answers the question. We can say that the limit as x approaches negative 2 of 3x plus 2 equals negative 4 because for any epsilon greater than 0, there exists a delta equal to epsilon over 3, that's where the value is that we just came into play with, such that when x plus 2 is less than delta, or you could put it, which is equal to epsilon over 3, then f of x, I'll put my function in there, 3x plus 2 minus that negative 4 is less than epsilon. So this is saying that when my x value is within epsilon over 3 of the number 2, right, when these values are close enough together that they're epsilon over 3 apart, then that forces the y value to be within epsilon of the number 4, negative 4. Okay, so visually, along my x-axis, I don't want to take the screen away, I promise I'll come back, but I want to do a visual real quick. Visually, back to this picture, we're saying, and again, I know all the numbers are different, but when we are within epsilon over 3 of the limit value down here that x is approaching, I will actually be within epsilon of the actual limit value that I'm saying exists for my function. That's what that definition is saying. Now, the beautiful thing in you writing that is that's almost what your theorem or your definition is that I told you had to memorize, right? So I don't remember exactly how many problems I have assigned. How many do I have there, maybe? 6 problems. So you're going to write a statement 6 times that looks like this, and we're about to write one more after this anyway. So after you've written it 6 times, portions of this you will remember, right? So that's another thing that's going to happen. Let's do the other problem that I've got here. It says symbolically find delta in terms of epsilon, so same directions, right? What about this looks a little different? Okay, there might be a whole or a asymptote because I have a denominator, right? So there is a denominator present here, and we think that that might actually cause something different to happen. How can we decide if something has a whole or an asymptote? Do you remember? Yeah, in a reduced form, right? So if I were able to reduce this and it cancels, then what do I have, Sam? A whole. And if it was not able to be reduced, then I have a asymptote. Very good. All right, so what do you think? Does this one reduce?
Yes.
It does, actually, yeah. So what does this become when I try and factor it?
X plus 2.
All right. So this actually reduces, and I get just the x plus 2. And so is the limit value correct? Is it 3? Yeah, it is. All right, so we're still starting and we're still working with the same goal in mind as we did on the other one. So we need to take the same original function. I'll write it originally how it was given to us. We want to take the limit value, which is minus the limit value, which is 3. And we start out with that being less than epsilon. What is the goal? What is it I'm looking for? Over here, like I did in the last one. Okay, so remember, it's the piece down here. It's the x approaching part. I need to be able to take that x value and subtract the value that x is approaching. In this case, the value 1. And that has to be less than some other number delta. This is my goal. This is where I want this right here to end up. Are we all good with that? Okay. Now, we already know that rational expression there, x squared plus x minus 2 over x minus 1, is actually the same as x plus 2 because we already did that part. So I'm going to reduce that. And then what happens on the inside? What do I have? It actually becomes the x minus 1. So it actually becomes exactly what I wanted, which means what's delta? It's actually epsilon. So that doesn't happen often, but it did happen on this case, right, that these actually matched because the inequalities matched at that point. So we found out that delta is equal to epsilon. All right, so we're going to write the statement about what we can show. We can say that the limit as x approaches 1 of x squared plus x minus 2 over x minus 1 equals 3 because for any epsilon greater than 0, there exists delta equal to epsilon such that when this case right here is where we start, when the x minus 1 is less than delta, or you can say what equals epsilon, it's less than epsilon, then the f of x value, that was that rational expression x squared plus x minus 2 over x minus 1, less than, or minus 3, is less than epsilon. In other words, when I'm within epsilon on the x-axis, it will force me to be within epsilon along the y-axis.
What is it? It says there exists. Is that a delta?
That's a delta, yeah, sorry. A delta equals epsilon. The delta equal epsilon, that's where we got to over here. Sorry, the screen doesn't always write for me very well. Any questions on that?